Okay, let's dive into the NVIDIA Nemotron-3 family of AI models. We're talking Nano,
Yeah.
Super, and Ultra.
Right.
And for you, the listener, this is more than just another model drop. It's really a blueprint for the next generation of specialized AI agents.
I think that's a great way to put it.
So our mission today is to unpack the tech that makes these models so incredibly fast and accurate, especially for these complex agentic workflows.
And the big story, frankly, is transparency meets performance. Nemotron 3 is pushing to, radically improve that accuracy to inference throughput ratio.
So better results, but faster and cheaper.
Exactly. And crucially, NVIDIA is doing this openly. They're releasing the model weights, the training recipes, and over 10 trillion tokens of data.
That kind of open contribution, it really forces the whole industry standard higher, doesn't it?
It absolutely does.
So that transparency is, well, a very strategic move. Let's get under the hood.
Mm-hmm.
The core architecture is a hybrid, right? A Mamba transformer mixture of experts design.
Yeah, and MoE.
For listeners who maybe aren't deep in the weeds with that, MoE just means the model has lots of little specialized subnetworks or experts, and only a few get activated for any given task.
Right. And the main problem with scaling these has always been the inference speed.
The memory cost, it just skyrockets.
Exactly. With a standard transformer, when it generates a long response, it has to store its entire history in this huge memory bank called the KV cache.
And that bank just grows and grows.
It increases linearly with the length of the conversation, so it gets prohibitively slow and expensive to run.
Okay, wait, hold on. Are you saying that with this new architecture, the memory cost stops increasing?
That's the core innovation. They weave in these Mamba 2 layers.
And how do those work?
Unlike traditional attention layers, Mamba 2 only needs to store a constant state.
A constant state.
Think of it like this. Instead of remembering every single word of a 100,000-word document, the Mamba layers keep a tiny, fixed summary of what's been said so far.
So the memory footprint just stays the same no matter how long the conversation gets.
Precisely.
And that's the breakthrough for speed.
That's it.
Because the memory doesn't grow, you get these huge throughput benefits. Like the Nemotron-3 Nano gets 3.3x higher throughput compared to a similar transformer MoE, like Qwen 3.
Which means your agent can process 3 times as many queries in the same amount of time. And that initial speed gain gives them capacity to spend elsewhere.
Which leads us to the bigger models, Super and Ultra, and this thing they call latent MoE.
Right.
So speed is kind of solved, at least for now. But with the bigger models, how do they boost the, let's say, intellectual horsepower without sacrificing all that speed they just gained?
By making the routing how a token finds its expert way more efficient. Latent MoE first compresses the token's information into a much smaller latent dimension.
Oh yeah, it shrinks it down before sending it off.
Yes, and that drastically cuts the memory and communication cost for routing, usually by about 4 times.
But if you're compressing the data, aren't you risking information loss? What's the trade-off?
Well, they mitigate that risk by immediately reinvesting the capacity they just saved.
How so?
They use that new efficiency to scale up the total number of experts and, more importantly, increase the number of active experts from, say, a typical 6 up to 22.
Wow, from 6 to 22.
Yeah. So by accessing more specialists, the model just gets more accurate. We're seeing big boosts on benchmarks like MMLU Pro, all while keeping that inference speed high.
This efficiency-first approach also enables these massive context windows. Nemotron-3 supports up to 1 million tokens.
1 million, yeah. It's staggering.
So for you, the developer, this means you can tackle enormous tasks, like having an agent review an entire code base in one go.
And that kind of scale needs really robust training. They didn't train it step by step.
Right. Not math first, then code.
No, they used multi-environment reinforcement learning. They threw everything at the model at once. Competitive coding, advanced math, complex tool use, all simultaneously.
And that turned out to be more stable.
Much more stable and effective at creating these versatile, reliable agents.
But I think the most fascinating feature, the one that really puts you in control, is this reasoning budget.
Oh, absolutely.
You can literally tell the model how much brain power, how many tokens for its internal thinking it's allowed to use on a problem.
Exactly. For a simple query, you set a tight budget for speed. For a mission-critical calculation, you open the budget right up for maximum accuracy. You get to optimize that cost versus accuracy trade-off on the fly.
So to sum it all up, Nemotron-3 is really defined by its hybrid Mamba transformer speed, that innovative latent MoE designed for accuracy, and the huge 1 million token context. And it's all open.
Which brings us to a final thought. Since these models are built for agentic AI and they let you control this thinking budget, It raises a really important question for developers.
Go on.
What are the implications when you can precisely fine-tune the intellectual effort of an AI agent, dynamically matching it to the complexity and speed demands of any task? You can essentially dial the intelligence up or down in real time. Okay, let's unpack this. Today we are diving into Opik, which is an open source platform from Comet. It's designed to tackle the entire life cycle of large language model applications. Our mission here is really to show you exactly how Opik takes the guesswork out of building and optimizing this stuff. Whether you're working on a simple RAG chatbot or those really complex multi-step agentic systems.
And that's the thing, right? Every LLM project, it starts in what you could only call prototype chaos. Opik exists because debugging, evaluating, and monitoring those complex workflows and already pipelines is, well, it's a nightmare right now. So they solve this by providing comprehensive tracing in these production-ready dashboards. It helps you move reliably from that messy proof of concept straight to a stable deployment.
Right. So if we follow that developer journey, it naturally breaks down into three core areas: development, evaluation, and then production. So starting with development, it's all about observability. This means deep tracing of every single LLM call, logging the full conversation history, and tracking all the context.
I mean, just imagine. That capability alone probably saves developers days of staring at nested API calls and wondering why their RAG response went completely off the rails.
Yeah, and Opik really shines by being extremely compatible. The sources mention extensive third-party integrations right out of the box, including recent additions like Google ADK, Autogen, and Flowise AI. That kind of support makes adoption, incredibly seamless.
Okay, which means you've built your prototype. Now you have to face that inevitable question. How do you automate quality control for something as fluid and subjective as a generative AI output? And that brings us to their second phase: evaluation and testing.
Yeah, and this is where it gets really interesting. You start with your standard data sets and experiments for automated evaluation. But the core breakthrough Opik highlights is this concept of LLM as a judge. The real insight here is that traditional metrics, like static accuracy, they just fail when outputs are creative or nuanced. So this judge model, a superior LLM, it steps in to evaluate complex, subjective criteria. Wait, hold on. If an LLM is scoring the output, isn't that just moving the goalposts? How do they ensure the judge model itself isn't biased?
It sounds like that, but it's designed to provide objective, standardized scoring for metrics that traditionally required a human to sit there and check. Things like hallucination detection, answer relevance, context precision. They enforce rigor by using these predefined, really detailed rubrics. Plus, for developers who are big on continuous integration, the PyTest integration means you can bake these sophisticated evaluations right into your CI/CD pipeline. It acts as a mandatory gate before anything gets deployed.
That systematic rigor is so crucial, but testing is only half the battle. If we connect this to the bigger picture, moving into production and optimization is where scale just hits you. And Opik is explicitly designed for that pressure. I mean, logging high volumes engineered to handle 40 million plus traces a day.
Well, 40 million. And that kind of volume stability is essential. But what happens once the model is live and facing the real world? This is where the continuous optimization comes in. They offer the Opik Agent Optimizer, which helps manage performance drift, and crucially, Opik guardrails.
The guardrails are key, aren't they? They aren't just logging errors. They are actively securing and enhancing the live application in real time, basically helping implement responsible AI practices by sanitizing inputs and outputs. It's the safety net every developer needs when they're scaling up.
Precisely. Now, for access, how do you get your hands on it? Opik is fully open source under the permissive Apache 2.0 license. You have two primary ways to jump in. The quickest path is through the Comet.com cloud, which they recommend for just getting started instantly. But for those who demand total control, you can self-host using Docker Compose for local dev or leverage Kubernetes and Helm for really scalable deployments.
And the codebase is heavily geared toward Python and TypeScript, which clearly signals their target audience. Data scientists integrating with modern web front-ends. So what does this all mean for you? Opik provides the complete toolset to move LLM projects from that chaotic, sort of hand-waving prototype stage to true production-grade stability and scale. It really forces a disciplined approach to measurement.
Which, raises an important question for you, the listener. Given that Opik focuses so heavily on generating objective metrics for failures like hallucination and context precision through this LLM as a judge idea, how does the ability to actually quantify these complex AI failures fundamentally change the definition of a truly production-ready LLM application? And if you do jump in, they encourage you to look into contribution opportunities, whether that's submitting feature requests or just improving the documentation.
Welcome back to the deep dive. Today, we're digging into something pretty exciting in the world of AI alignment.
Yeah, we're looking at a huge new human preference data set. It's called HelpSteer3-Preference, or HS3P for short.
And our mission is to figure out how this data set is basically providing the high-quality fuel for the next generation of LLMs through RLHF. That's reinforcement learning from human feedback, of course.
Exactly. And the thing is, this isn't just a small step. The impact is, well, immediate and pretty staggering.
Staggering how? Give me the numbers.
Okay, so reward models trained on HS3P just shot to the top of the leaderboards. We're talking 82.4% on RM bench and 73.7% on judge bench.
Wow. That's, what, a 10% absolute jump over the previous models?
The 10% jump, I mean, that's like a year's worth of research progress happening overnight.
That's huge, but is that just about making the data set bigger, or is there something else going on with, the quality?
It's really the synergy of both. The scale is definitely a factor. It's over 40,000 samples, so 4 times bigger than its predecessor.
Okay.
But the real key, I think, is the precision. They didn't just scale up. They added really diverse and valuable categories, things like STEM, coding, and even multilingual tasks.
So that implies they had to be really careful about who was doing the annotating, right? This couldn't have been a general crowdsourcing job.
That checks out completely. They used specialist annotator pools. So for the STEM data, the annotators actually needed to have degrees in relevant fields. And for the coding tasks, you had to have actual software engineering experience.
Right, so real domain expertise. And I see that expertise also extended globally, which feels critical.
Oh, absolutely. Almost 20% of the samples are in the multilingual set.
And that's not just 1 or 2 languages.
No, it's 13 different natural languages. And we see a lot of Chinese, about 30%, and then Korean, French, and Spanish are all around 10% each. So it's not just an English-centric model of preference.
Okay, so that global reach is massive. And I think that's where things get really interesting, because the way those different language pools annotated led to some very different model behaviors.
Exactly. It led to 2 main models, an English RM and a multilingual RM. And what's so fascinating is the stylistic bias they uncovered.
A stylistic bias.
Yeah, especially in the English model. It was, let's say, surprisingly sensitive to things like how long the response was, or if it used a lot of markdown formatting.
So style over substance, almost. What was the big aha moment from the testing? How did they prove this vulnerability?
Well, the researchers set up this clever test. They took a concise, correct answer that was chosen by a human and pitted it against a verbose, nicely formatted answer that was rejected.
And what happened?
The English RM's win rate just plummeted, a 24.8% drop. It was essentially fooled by a longer, flashier response over the better, shorter one.
25%. That's a huge vulnerability. It's basically an exploit waiting to happen.
It really is.
So how did the multilingual model handle that exact same test?
This is the profound part. It only saw a 6.4% drop.
Whoa!
Yeah. It suggests that the multilingual annotators were just way less biased by those flashy, stylistic things. They were focused more on the core content, not how it was dressed up.
So different cultural ideas about what a helpful answer actually looks like. One values detail and format, the other values substance and conciseness.
It seems that way, yeah.
So if we pull all this together, the performance jump, this wild stylistic split, what's the big takeaway here for the future of alignment?
I think it shows we've made incredible progress on the data volume problem, but in doing so, we've exposed this really subtle new challenge, which is that if even expert annotators sometimes prefer style over substance, we risk training models that are just really good at, sounding helpful without actually being helpful.
Right, masters of formatted filler. The ultimate goal is helpfulness, after all. So this leaves a really important question for you, the listener, to think about. How do we get alignment methods to better reward that true helpful substance, especially when what's helpful totally depends on the user? A novice might need that long, detailed answer, while an expert just wants the facts. That tension, that negotiation between substance and style, that feels like the new frontier.